start with the caveat, which is, and I hope this will work, that this is not, is neither a comprehensive or complete set of items under this title, but rather a collection of thoughts that have been accumulating for a very long time, and I thought I'd get them down before the neurons die. And so I don't have too many slides, and I might skip some because I'd like there to be conversation about the ideas. So I'm going to do two parts. The first one is rather general, just how would you approach this issue and why is it a problem and all those kinds of topics. And the second part is to use clouds as a thorny example of what one might try to do. So here's our situation. And the first line there may strike some people as odd, but for those of us who started some time ago, when we first started the climate business, that statement wasn't true. There were essentially no data sets. So now there's an embarrassingly large pile of data sets which are pretty much being ignored. So that's part of the situation. And the second one is the complex model may be sophisticated, and the complexity is growing rapidly as people move on beyond purely atmosphere to coupled atmosphere ocean. Pretty soon there's going to be political systems included in the earth science models, and so coming to a neighborhood theater near you. So we have a lot of data products, and I emphasize the word product because part of the problem had been that if I give you radiance measurements, so what? You know, you can't really infer much from that. And although the weather guys seem to think that's what they prefer, but I think if you're going to really evaluate a model, you want things that represent geophysical variables. So products are things that people make from raw data with more or less quality. And so the problem is a very large number of products, including multiple copies of supposedly the same measurements. Okay, so the challenge is that the climate system is all of these words. And I'll just emphasize for the students in the audience that nonlinear isn't just y equals x squared kind of nonlinearity. It's this business. It's non-locality, it's intermittency, it's all kinds of fancy words that mean it doesn't behave anything like Gaussian statistics. And the crisis of large degrees of freedom or high dimension prevents a total analysis. So here's what people tend to do. This is my favorite phrase, the blob comparison. Here's a map of my model, here's a map of some observation. You're supposed to believe that they're similar. So we try to at least get people to do difference maps and linear correlations, which is sophisticated analysis, right? When you see linear correlation, it's usually at best bivariate, even though multivariate linear correlation is easy. It's in MATLAB, you can do it, but people don't. And at least in climate world, but even sometimes in weather world, there really is no looking at the dynamics. So in weather world, to the extent that they look at dynamics, it's a case. So you can't make any statistical or general statement. And in climate world, the focus is on interannual variability. And I was very deliberate. I almost changed that word. But in fact, people ignore the seasonal cycle typically, which is a form of slow variability you could check. So I'm going to propose some things to try. And this one is sort of asking yourself the question, here you are, you come up to a table and there's a box sitting on it and it does things. How do you come to understand what rules it follows and how it, what it might do in the future. So we can first just characterize variability, and I would submit that the piles of products we have gone far beyond the early characterization of variability from say temperature and humidity and even the winds to many, many more variables, and that has not been really pulled in. You can try to figure out why the box does what it does. And I'm going to, on the next slide, say that one of the things you can do is say, what is its forced response? If I push on it, how does it respond to that? But one of the features of a highly nonlinear system like this is it can vary with no forcing at all. Although actually it's just a form of nonlinearity, that there is variable forcing and it's being communicated away from its original space and time scale. And then we'll talk about how you get at processes in a minute. So this is an old, out-of-date slide, but I just wanted to make this point about what's available. And the actual bars go up to at least 2009 or 10. And we're now, the GWEX group is about to release surface evaporation and sensible heat flux products. And so by the end of this year, we'll have all of this stuff on the same grid, same time step for 20 years roughly. And so you will really have everything you need to describe the exchanges and fluxes of the energy water cycle, including the state properties. So it's a rich environment, so the rest of the seminar is what do you do with it? So here's the simple physicist's approach to a complicated problem is start with forced responses, if you have them. And I almost left out mean heating, which may not sound like a forced response, but we have to remember the basic state is the average heating of the Earth, which sets up a mean circulation in the atmosphere and ocean and all the things that follow. So even just the latitudinal dependence of that should be checked. Then there are two forms of solar heating variation, diurnal and seasonal. Those are the two frequencies. But this stuff aliases to the rest of the spectrum in space and time. Then we have some slower things like volcanoes and solar cycles. And then I note that you can focus on the atmosphere on sort of decadal time scales or interannual to decadal time scales, and then you can treat the ocean as a kind of forcing for the atmosphere and see what it does. And we now have long enough records that we have more than one of these events to look at. But as I said, there's unforced variability, and there's at least two primary instabilities driven by energy, the heat engine, convective, and I'm thinking of a small scale, convective and baroclinic. But there are some other wave dynamical instabilities that may be operating. Maybe the MJO is a result of that, and I'll talk about cloud dynamics. So a very simple thing to do would be to set up a set of standard diagnostics and evaluate these things. And here's the key: every time you change your model, do it again. You should be constantly monitoring, but actually most of this has gone out of fashion. The GISS model we used to brag on it, had inline diagnostics on many of these things. I don't know how many people are looking at them today, but it used to be what you looked at. So it's not everything you can do, but it's these are the sort of interval constraints. Does your climate system behave the way it's observed to behave? Does it have the right statistics? It isn't just, does it have convective instability? Does it have the right space-time spectrum and distribution of convective events? And I'll show you at the end an example of the fact that current models do not. But even good old baroclinic instability, which we think we totally understand, do we actually have the right distribution of cyclone strengths? So this is something you should just do, and it should be a standard diagnostic, and all the models should compare to this. But look at the IPCC and other kinds of model comparisons and activities, and you don't see much of this kind of stuff. You see monthly mean blob maps and other things. Okay, here's an oldie but goodie. We have a theoretical framework that says this is the internal energy cycle. I was talking about the energy and water cycle before in terms of radiation and water exchanges and so on, but this is the dynamical cycle. And Tony's done some work on how this changes when you're on a different planet. But we should be checking this stuff, and now we have the capability to estimate quantitatively the generation terms, but also measure from reanalyses or something these conversion terms. So how does the model look, and how do models compare? This is a basic characteristic of the model. And this is my feedback, but I'll go on. So something I don't see is, and this is maybe a generational problem, but models have become simulations and not what they really are, which is computer-assisted solution to equations. So the goal of the science is the correct equation, not the correct simulation. If you have the correct equation, then the simulation, there are some technical numerical issues in getting a good solution. But instead, the focus of attention seems to be on tweaking what's in the code without sort of thinking about the fact that you're trying to verify an equation. And so, in particular, people don't look at tendencies. But the code says d by dt of something equals a bunch of stuff. And yet nobody's checking the d by dt, yet we measure it. Okay? So here's some possible things that one could do to look at the equations. And so I think my next slide is the equations. And the only point of this familiar set of equations is that you don't see many terms in these expressions that depend on the variable itself. It's derivatives of stuff. So when you're comparing, you should be comparing time derivatives. You should be comparing space derivatives of quantities, not the value of the wind, but the derivative of the wind, the shear. And you can add more things, you know, d cloud dt, d aerosol dt, and so on. And the goal is to verify the stuff on the other side of the expression. So some of it's Navier-Stokes, and we think we know that, but when you get down to energy, you have something here which is all kinds of processes that are not fluid dynamics. You have evaporation and precipitation showing up as processes. So we should be verifying the equation that's in our code. Better yet, we should verify the true equation even if we have to parameterize it for the code. But I don't see that sort of approach to process. So I'm going to get through the cloud part of this quickly so we have time to talk about it. But that's sort of a general set of things that it's not that any particular modeling group isn't doing these things. If you look at the community, they're not organized to do it. There's not a consensus of which of these items or alternatives should be the focus of attention. There's not such a consensus. So let's pick a case of a process, clouds. And if I had the movie version of this picture, and you were from some other planet, you would know right away that you were looking at fluid dynamics. It's easy to tell. So essentially, clouds are a fluid dynamical creature. Yet the way in which we use the data, first thing people do with the ISCCP data is take the monthly mean, which throws all the dynamics out, basically. So how can you come to understand what this is about if the first thing you do is average all the dynamics out? So I point out that, for instance, clouds are not an equilibrium condition. They're a metastable state. And even if you look at the arrows coming in and out of a cloud, water in and out and so on, particles in and out, they're not even in balance. They're a dynamic quantity. So it's the time derivative is as big as any other term in the equations. So how do you handle observations, and what diagnostics do you get from your model to demonstrate that you've got the right equation for the time derivative? That's the question. So here's a couple of possibilities. With a metastable state, there can be thresholds. The two that are important to clouds are phase and the size at which precipitation occurs. And there's, of course, two phases and two kinds of precipitation. So we should be trying to analyze the data to figure out what those numbers are and checking our models for those numbers. Does it start to precipitate at the right particle size? Does it change phase at the right temperature under the right circumstances? Okay, I'm going to skip the slides, but I just wanted to say one way to estimate these tendencies from a complex data set is to use a statistical approach. You train it. For example, you can train a neural network to mimic the time dependence of a set of variables all simultaneously, and then you can ask whether the model does the same thing. That's never been tried that I know of. And we thought this might be a really cool way to get at these relationships until we tried it, and we actually got the model run from Ron. Asked him, I said, does anybody have a 10-year data set of time step resolved data? Because we couldn't use monthly means. So Ron turned out to be the guy who had one. And first we had to overcome the technical problem that he didn't have a disk drive big enough. And it was all of 10 gigabytes. Oh my God. Okay, so today storage is essentially free, and volume is not the issue it was when we were starting out, and so you shouldn't be afraid of a few terabytes. You really shouldn't. The computer doesn't care. So we did this method, we applied it, and it worked fine mathematically. The model, pushed the model through, trained it all up. The problem was we couldn't interpret the result. The result was as uninterpretable as the original model itself, in the sense that, because we had only 22 variables, I think, going simultaneously. So I'm going to say, let's think about some other ways to reduce the problem and get at what's going on. So here's one. And conditional sorting is actually extremely trivial and little practiced. I don't know why. People seem ready to average, but what they basically do is average each element separately. So if you think about it, if two things are related to each other and you average them separately, you've broken the relationship. So how can you figure out what the time derivative process is if you've done that? But that's what people are doing with the data. Conditional sorting just says be a little more intelligent in your averaging, and one way to be intelligent is say, let me define different meteorological events by some criteria, and then now average my data, but by meteorological event. So here's one example we've been working on, which is cyclones. Mid-latitude cyclones, the simplest expression of their existence is an isolated low pressure minimum, surface pressure minimum. And so you can track all the cyclones, find all the cyclones, track all the cyclones, then composite the data centered on the cyclone centers. That's what this picture is. And it's, let's see, it's cloud top pressure over here, optical depth, the net flux in the atmosphere, so the radiative diabatic heating and the crescent. So this was our first attempt, and already some interesting stuff comes out. In fact, you can see the cold front, and if you look at an instantaneous realization, it's much more obvious. And so one of the problems with this is that cyclones come in different sizes and shapes and so on, and it smears the features out. But this is already more informative about cloud process. In particular, notice this backside low level cloud, which any meteorologist knows about. But the whole idea that the high cloud is out here in front of the low pressure center and there's this backside low. And really what's interesting is the medium level cloud back here, which does all the snow fall in winter. So the snow falls off to the northeast. So you can begin to understand what's going on with this simple averaging, but with a little bit more information. Well, the new results we're working on, one of the things I wanted to highlight is here's a distribution of size, but it also is proportional to strength. And when you see a skewed distribution like that, you know two things right away. You can't use Gaussian statistics, so averaging is misleading. Up front, it's misleading, because all I have to do is add one guy here and I change the average. So the average becomes more, people average data because they think they're reducing the sensitivity to things like sample size, error, and so on. When it's a distribution like this, the average is very sensitive to those things. So it's doing the opposite of what you think you're doing. But the other question is, so why does it have that shape? It could have some other shape. Obviously, it doesn't go below zero size. And actually, what you're seeing here is two different reanalyses with different spatial resolutions in their underlying model. And the one with the higher resolution has a peak at smaller sizes. Not a surprise. Well, here's a story. I don't know if it's true, but just to show you the kind of thinking. What if a totally dry, cloud-free, rotating Earth with the same forcing, therefore it has baroclinic eddies, produced a distribution that looked like this, and stopped here? And what if cloud processes and moist processes and diabatic forcing from clouds is what creates this tail? Then A, you'd want a climate model to do that right, not get the mean correct, but do the distribution correct. And secondly, you'd want a weather model to predict accurately that transition from weak to strong. And so if you do a conditional sorting by storm strength, here's the long wave TOA flux and the precipitation for weak, medium, and strong cyclones. And so, as you might expect, more precipitation in strong storms, but also a very different long wave perturbation in the radiation. So what if the climate story is that these guys are kind of a wash and really don't do a lot except transport the heat forward, and these are the characters that affect the radiation budget or produce almost all of the precipitation. So if a model doesn't have this distribution, it stops here, then it doesn't produce the right distribution of storms, it doesn't produce the right precipitation under the right circumstances, it doesn't respond correctly. Okay, well, here's a convective case, and we provocatively named regimes defined by the pattern of cloudiness as weather states, but that's not totally crazy if you look back before numerical models and even before Rossow and company started doing map analysis. The way weather was predicted in mid-latitudes, at least, was by looking at the clouds and seeing what was happening and then knowing that tomorrow something would follow. So just for those of you who are unfamiliar, we're talking about cloud top pressure, optical thickness, distributions, and here's the tropical set. If you do a pattern analysis on these, you get these 6 patterns. So in other words, the variability of cloud mesoscale patterns can be reduced to just a variation among these 6 shapes. Okay, so we called those weather states, and actually some other follow-on work showed that indeed the temperature profile and other attributes of the atmosphere are different among these states. And just to get you oriented, something up here in the corner like that is very high, very optically thick. It's a convective, deep convective cloud, and something way down here is a stratus, and this is a trade cube of some sort. So when you map them, and I've got the map, but I won't show it, when you map them, they fall out in places where we already knew ahead of time that certain types of clouds tended to be predominant. So what if you start sorting your data sets by that? And here's one example. This red curve is the complete distribution of rainfall intensities for the tropics, and the green and blue curve are the 2 kinds of deep convection, and the purple curve is everything else. And what this shows you right away is that everything that's called heavy precipitation is produced by a specific type of tropical system. And what makes that important is that that particular type of tropical system doesn't exist in any GCM today. So here's an example, and notice we plotted this on a logarithmic scale, so if I plotted it on a linear scale, it would look more like that cyclone strength, big, long tail out to large values. So these guys are rare, a few percent of the time, but they're doing all the work. So the tropical heating is not produced by some average of all convection. It's produced predominantly, Bob Howe says 90% of it's produced by these organized mesoscale systems which don't exist in any model today. So how is that model going to respond to a change of forcing if it doesn't have this degree of freedom? It has only this blue curve here. So that's an example of what I mean by breaking the data down beyond the average and trying to look for structures and patterns, because that's ultimately what you want to put into your model. You want to tear it apart until you can verify the equation. So the model's going to need some change to have a type of dynamics it doesn't currently possess. Okay, 2 last slides, which are fun. If you're in the weather forecast situation where it's an initial condition problem, and therefore the time scale is pretty short, you can always verify your forecast. Okay, because you can look at the data next Thursday, and check against your forecast. And that's what people do routinely. But it's not very detailed. In fact, they tend to verify against only what they observe and put into the analysis that set the initial conditions for that model forecast run. They only tend to look at those variables. They actually secretly look at precipitation, but it sucks so badly that they don't mention it usually. But I've asked around, and they're not verifying tendencies, which is interesting, even though that's deep in the analysis machinery, and especially when you do 4D VAR. The tendency is a very specific thing you work with. So You can test the sensitivity of your model to the observational accuracy, or likewise, does your model accurately do things? And you usually blame the observations for the problem, not the model. And you can also test model parameterizations and verify because you're verifying your forecast. So you can ask, how sensitive is my forecast to that piece of physics, and whether I do it right or not. Of course, the limitation here is that some physics doesn't do much on a time scale of a few days, and the classic paper is Barry Hunt's paper from '76, where he took the state-of-the-art forecast model and turned the sun off, and it made no difference to the forecast. Of course, it was only a 3-day forecast, so you can understand why that's true. The sun doesn't, in fact, matter on 3 days because you've already given the model as an initial condition all the temperature and energy it needs. So it's got all the momentum and energy, and it doesn't really run out for a few days. So this can test fast processes like clouds, okay, even aerosols and chemistry and so on. This is a good framework for that because they're fast. And here's the climate model equivalent of this page. Problem, if you're talking about decade or a century from now, you don't have any observations. You try to reconstruct things from paleoclimate, but the number of variables you have is very limited, so it's not clear you can get a unique answer here. So you can again test the sensitivity to observation accuracy and then blame the observations. You can also test to model sensitivity parameters, but you can't verify in the climate context. So the last pitch, to go back to the slide of data sets, we now have, and will have by the end of this year, a 20-year data set that has all the energy and water terms in it. We have longer data sets for other things that go back at least to 30 years ago. So now you can at least look at the model's climate variation on that time scale of decades. And the Pinatubo experiment, for example, is another transient event. And for, practically speaking, you may argue that the primary political concern about global warming is the next few tens of years and what's going to happen. If that's the case, then you now have long enough records to actually test the model's behavior, even if you can't test its trend. So I'm not really necessarily talking about some trend over 30 years. I'm talking about, let's take a look at ENSOs, let's take a look at the PDO, let's take a look at various variations and see if we can discern how cloud feedback, for example, works. Okay, so that's a loose collection of thoughts, and I wanted to spend the rest of the time, opening the floor for people's ideas, yay or nay. Yeah, Andy.
Are the clouds doing anything different today than they were back in the 80s?
Bastian asked me that. As you may know, the ISCCP says the global mean cloudiness has this sort of slow variation over its 25-year record, and some people have, and as I said, there seem to be two groups of people in our field: those who believe any variation on that time scale must be false, and therefore all data sets should be featureless over decades, and the other group that believes any such variation must be true without question. And the third group doesn't exist, the group that thinks that an accurate data set that has no variation is also interesting. So the answer to your question is yes, they're slightly different than they were at the beginning of ISCCP. The global cloud amount is down by 1% or so. It's mostly low clouds at the optically thinner end. The rest seem more or less the same. I haven't dug any deeper than that, but that's what I can say so far. So here's this slow variation. Pretend it's real. Why does it happen? Well, the interesting suggestion is the PDO changes sign at either end of that record.
there was a story a week or so ago about cloud heights decreasing over the last decade. Is that right? Do you think that's right? And my assumption was it might be related to the fact that 3 out of the last 4 years have had strong La Niñas.
So I haven't looked at it that carefully. If you look at my data set, without question, it suggests that cloud height has increased. But we know that's spurious because the atmospheric temperature profiles I use have a spurious variation in them. So if you look at cloud top temperature, which is what I measure more directly, there's no apparent change. Now,
Whose paper is this?
I don't know, about a week ago it came out.
There's some guy from New Zealand, they're looking at MODIS. And
Miser.
they're finding a slight decrease in cloud top pressure in MODIS when you take global
slight, but
warming.
how big?
It's,
I think they're looking at Miser data, maybe also Modus, but at least
yeah,
Miser.
or a combination.
But it's very different.
But it's a global mean value, which is.
I mean, the problem with those who believe without question is, of course, that they have no sense of proportion. So any change is real. So how big is it? How much, what are we talking about here? 10 meters? I don't believe our accuracy is that good. Can there be systematic effects that mimic such a change? Yes. You have to be very careful when you start looking at something so small. And that's why I sort of emphasize using the data sets to do processes, because the signal is much bigger and the errors are less of a problem. But if you start saying you want to measure 1% changes over a decade, then things like MODIS's sample, for example, I'd have to know which cloud top pressure if it's MODIS, because there are two. If it's Miser, which Miser? Because Miser is a horribly subsampled data set that's darnally aliased. So all I have to do is delay the clouds a little bit, and I can change the height. It's not the same kind of change at all. So the Miser data set is very poor sampling. We're doing an international comparison right now of products, and the first thing we learned is that Colder and Miser and Calypso and CloudSat, just forget them. You can't believe their monthly means. Their sampling's not good enough, and it's too biased.
Because the swap width is
Both the swath width and the fact that the diurnal aliasing and the fact that they don't tell you the answer for every pixel they see, they select. Which means then you have to ask, well, how did they define that subset? And sometimes they can't. MODIS does that for its optical depths, for example.
So a longer average would be better, or
Yeah.
not average?
Yeah, it's partly just total sample size that they don't have. So if you go to seasonal, they might be trustworthy. But I wouldn't believe them at monthly level. But
If you don't resolve the diurnal cycle for clouds, it's
well, yeah,
so.
yeah. I mean, it's even worse than a single sun sink polar orbiter, which at least has two samples. They got one per day, morning. So it's horribly aliased. And if you look at something like land-ocean cloud amount difference, they're different than every other data set that has some sample of the diurnal cycle. But this is even just a raw sample size problem. Their monthly means are very noisy. So, George?
Going back to Andy's question about how clouds are different from the 80s, I mean, other than processes like storms and weather states, we did look at some trends lately. So we have one paper out that shows that tropical convection increased in the 80s and 90s and then leveled off after 2000 for the last 10 years. And that sort of went along with a paper by Susan Solomon, which showed that the lower tropospheric water vapor,
Stratosphere.
lower stratospheric water vapor increased in the 80s and 90s and leveled off after 2000, and she attributed part of the slowing, or whatever you want to call it, of the warming to this change in lower stratospheric water vapor. But we do find a leveling off of the increase in tropical convection. So that's one trend we've looked at, and then there's another trend which there's a paper that came out recently, but we have more work coming up, which we see a very pronounced poleward shift in the clouds, which we attribute to poleward shifts in baroclinic storms, in the baroclinic storm path in both hemispheres. And so those two, I think, are very significant trends that we find in the data, and I think we're fairly certain that they're robust because we've analyzed the data in several different ways.
But there's two things you can say. So one, yes, there's variation, and there's some slow variation, which we don't understand. And two, you have, as I say, you have to be very careful about these things. It's almost surely nothing we're seeing is a global warming driven thing, as far as we know. It's too short a time scale. So you can't tell what's going on. You know, if I show you a variation like that, you might, oh my God, it's something, but then I show you the second half and it does this. Well, you know, now it's a sine wave. Well, wait a minute, now I show you a longer record. So the longer the record, the more your impression of what you're looking at changes. I mean, people don't see in Fourier space, but they should learn to do so. So if you have a record length of 20 years, you can't say anything about variations longer than 10.
Slight objection with the poleward shift of the clouds, I think. I mean, both theoretical arguments and lots of models
Might
show
be.
that it may
Might
be
be.
related to global
Might
warming.
be.
So Bill?
Yeah.
So you talk a lot about comparing processes in models and observations. You talk less about what exactly you would compare, what quantities you would compare in models and observations. There are two religions out there. One religion says that the remote sensing community should retrieve geophysical parameters from their radiances, activity, whatever, and then compare those to the geophysical parameters the models actually produce. And there's the other religion that says no, the model should run instrument simulators and produce the radiances and reflectivity and compare those. What's your opinion of that?
Well, so firstly, the interesting history of the instrument simulators is that the ISCCP one is the only one that does what you said first, namely geophysical variables to model. All the others take the model's variables and simulate radiances. And it's the same problem of any remote sensing retrieval. It's not a unique relationship. So you do it, and your radiance doesn't agree with the observations. Now what? You don't know which line of code to change or which variable is wrong. You may, in some cases, have a pretty good idea because that variable is dominant in the signal, but you're always left with the problem of, can I uniquely identify the problem? So that's why I said go back to the equation and verify the physics you're trying to write down. So, for instance, like I said, a simple example is cloud water and particle size versus precip onset. We know from 50 years of laboratory and aircraft and ground-based cloud microphysical studies that there are thresholds in those things for good physical reasons. So does the model have the right threshold? And there's always the parameterization issue. But so my short list is back to that list of forced and unforced variability, followed by, if I'm doing the cloud problem, is I'm looking at when does it precipitate and how does it evolve dynamically. So the other kind of work that I didn't present is resorting the data in a Lagrangian framework so you can follow an air parcel or a storm as an entity and watch how it evolves, and then ask, does my model do that? And that kind of sorting of the data can easily be done to the model as well. So if I were to tell you, I mean, for example, that histogram of cyclone sizes, as I said, is a histogram of cyclone strength, i.e. the depth of the central pressure. It's also a histogram of cyclone lifetime. So does a model get all those things right? That's question one. Question two is, does it get the right type of cyclone under the right conditions? So now you sort by strength the state of the surface and atmosphere and find out if there's some way to predict which one you're going to get. then you can ask the model to do that correctly. So something along those lines. And I think for me, the cloud question is largely, do we condense the right amount of water and precipitate it out, and do we condense it for the right amount of time? Something like that.
So our both are orbiting satellite data. Are these of any use for these things?
Well, this is the thing I've been trying to advocate for 15 years now. There is a data set which has higher time resolution, ISCCP, so you can use it to rearrange the polar orbiter data. You can't defeat the diurnal aliasing, but you can say, how old was that storm when I saw it? And rearrange your data in sequence of age. So it's a statistical trick that can't work for every type of system. For example, ISCCP's time sampling is 3 hours, so you can't do that for an individual marine cumulus blob because it happens too quickly. But there are games like that. But by the way, you know, in the archives are 15-minute imagery. We've got 30 or 40 years of this stuff, which no one has processed. So if we really wanted to do cloud dynamics, that's the next data set, is to process the hell out of the imagery we have to allow us to sort the more, the better measurements, if you will, in the sense of they measure attributes the imagery doesn't give you, like vertical structure, like particle size, all those kinds of things.
Have you looked at data that lets you make a general conclusion about how realistic the GISS model can simulate volcanic processes?
We haven't done that yet. I mean, Mike did for his thesis, at least with the water vapor part of that story. And we've looked at these composites a little bit, but we're sort of on the verge of doing that in the sense of, first we had to get the data organized.
No, I mean, we have a couple of papers. I have one, old one, and Tony has a more recent one. And part of the conclusion is GISS, as well as many other models, tend to make bullseyes of high thick clouds where the low pressure is, and then very little along the fronts or in the backside of the cold air outbreaks. Tony can say a little more about that.
Well, we've also, I mean, look, using CloudSat data, Katrina, which is here and now, and then Jim Booth, so Jim
There.
behind us. Oh.
No, it's right.
Oh, there you go. Yeah. So we know what the vertical structure do a bunch of storms looks like, and our models, storms are too shallow, and for whatever reason, they have a hard time getting moisture up into the atmosphere so the clouds can form high, and to what extent it's a problem with the model circulation, to what extent it's a problem with cloud parameterization, we're still working. But we know that when you get into the mid-troposphere, our latitude storm clouds and so on, associated with the amount.
And that's the first step, is the sort of static characterization, if you will. The next step is the distribution of storm properties, not just the average. And the third step is the time evolution, so that you can figure out where your problem's coming from.
Yeah.
And we, yeah, go ahead.
Well, I looked at the distribution of the strength, and we don't get the strong ones. I looked at the distribution of duration, and our storms are actually lasting longer than the ones you see in the analysis.
Yeah, so
They have done
in
a
an
little bit-
integration,
they have-
maybe.
They have done a little bit of what you were talking about in someone else's question about age of things. And that they are using the reanalysis information, which is the circulation equivalent to ISCCP, that's there all the time and resolve the complete cycle of things. They can identify when storms are beginning, when they're at their peak, and when they end. So they can actually look at,
Yeah, and that's
in a
what this
statistical
comes from.
sense, at the evolution of the clouds in the storm, and see what they look like at storm onset versus the.
But, I mean, I'm sure Bill is gonna make the comment, but look at the difference when you look era 40 versus NRA 2.
Era interim, actually.
Era interim versus NRA 2.
Yeah, this figure is the comparison when you take only the cyclones they both see. And this figure is when you include their total set of cyclones. So ERA has more small objects. And somewhere down here you start to worry that it's an artifact of the model grid. So we
What
don't
about-
really know where this edge should be.
What about the geographical location of volcanic storms and the storm tracks?
It's fairly, I mean, most models put the storm tracks over the Atlantic, over the Pacific, and over the Southern Ocean. That's not-
But the answer is there's an
Not
awful
much.
lot of those details that now could be checked.
In the-
And some of the information to do it has been around for 20 years.
But we started looking at light to cloud shifts in the model in the last 30 years, and interestingly enough, I mean, I'm going to show some results in a month or two, but when we're finished, but they do show a poleward shift similar in magnitude to the ones we find in the observation, which is fairly encouraging in terms of simulating the feedback school.
Yeah, I mean, that's part of what inspired some aspect of this study was a model paper that said, okay, we did our global warming experiment, and here's what our model says about the distribution of storm strength. So do we have any evidence that that makes sense? And that's where we're headed to try to verify that. But the hard question is, let's say we compare to a model and it doesn't agree, or even if it does agree, the question is why? You got to dig into your code and say it agrees or disagrees because. Otherwise you can't fix it. And just because you agree may not really mean you do it for the right reasons. So you said you had a pretty good distribution of your sizes were too small, but your lifetimes were too long, which means plotting those two against each other the way we do in our paper, you're going to be on the wrong straight line. So, but what determines that? What determines a baroclinic eddy's lifetime? It's a good question. Yeah.
How does Iskip series compare on the global radiation budget?
If we do the average our brains out global monthly mean type of thing, our top of atmosphere calculated fluxes are within a few watts per meter squared. Regionally, there's some bigger errors, which we think we know what the cause of that is. It's not the clouds, it's the atmospheric temperature, humidity profile that's screwed up. The one we use for the calculations. So we're trying to make a better one. So we can get regionally, take regional monthly means, the RMS differences are sort of 10 watts or so. We have better sampling than they do, although they attempt a correction. So we're about where I would think, given that the products we're using for the calculation aren't that good. So it's surprising we got that close, I think. So we're now in the throes of revising everything and hoping we can take out some of the known problems and increase the accuracy. It's a remarkable thing to discover that there is no credible temperature humidity data set for the globe. Full stop. There's weather models and reanalyses out the wazoo, but if you look carefully at them, they don't agree with the observations. So and then wait a minute, you look at the observations carefully and they don't agree with each other. So we really don't have a good atmospheric temperature data set, especially near the surface. I think one message I would give is that, of course, the infinite variety of things one could study in a model tends to leave you going, oh my God, what do I do? And what's lacking, I think, is some kind of discussion that goes like this. If I'm gonna believe the model's forecast of the next decade's climate, and I have to tell you what aspect, is it just the temperature or is it the the precipitation or what? If I'm gonna believe that, then what else should it do right? There should be a community set of standards that starts to build that says, look, if we're gonna believe your forecast for this, then you should do these things right. And so things like storm distribution strength and that stuff hasn't even been done really. Not even for weather models. I mean, they think they're doing okay because they do cases. But you know, of course, of all the cases where the forecast fails because the model doesn't produce this tail. So the forecast is right a lot of the time, except when it's not right. And unfortunately, the case where it's not right is the one we're really concerned about, which is the storm that eats your city. So there's all kinds of theories about why that's so, but I don't see anybody. I've been reading papers trying to find out what's known about the energetics of these storms, and over the last 20 years, there's maybe a dozen papers. So it's not really a hot topic. Nobody really cares about why that tail exists. Exactly. I once was in a meeting where we raised the subject of metrics for climate models, and first there was deathly silence, and then somebody named Bill started down his list, and they said, okay, enough, we're going to talk about something else. So they don't really want metrics.
Well, but there's a substantial community now that does want metrics, but the problem, I think, is that they just want to, by fiat, say these are the metrics without actually connecting them to anything that the climate model really wants to predict.
Right, right. And I think, I mean, some of the stuff here in the first part of the talk with, about the energy cycle and that sort of thing, I think you can now do, with this data set coming, you can do the complete energy and water cycle and its variation from diurnal to decadal, and that may be done accurately enough that we can start discriminating against some models and saying they just don't do it well. And I would submit, if I'm predicting a change in climate, which is an energy-driven change ultimately, because CO2 just changes the radiation balance a little bit. That's an energy story. If the model doesn't do its energy cycle right, I don't believe it's forecast, even for temperature. So if we could get that far, it'd be a big breakthrough. Then there'd be fun things like, is there anything about the model's behavior that connects to its sensitivity? And you're seeing some hints of that in the storm shift thing, that the more sensitive model, I forget which way it goes, but the difference in climate sensitivity appears as a difference in how much they shift. And there may be some other cases like that, so that begins to provide discrimination also.
Huge differences. 2 degrees of more shift, forward shift, you can get almost 2 degrees more sensitivity.
Yeah, so the larger the shift, the more sensitive the model.
All the AR4 mostly, but
Yeah,
lots of AR4 models, and the relationship is really forward cloud shift and model sensitivity is like 90.98 correlation coefficient.
But you don't know if the AI applied models.
No, but we're about ready to start looking at the AR5.
Okay, spend enough time.